begin his lecture.
Thank you, Jugal, and I'm very happy to be speaking here. That this is a project I've been working on over the last few years, and I have something that's I've done quite recently, which I guess I'll talk about in the second lecture. The setup in here is I'm going to have always talk about R with the maximal ideal M, Noetherian local ring. All rings, local rings in this talk are Noetherian. And I take what is M filtration. So I'll define that because that's very important. And M filtration is a family of ideals I, which is I sub n, which has the following properties. First off, R is I naught, which contained in I1, I2, and so on, where I sub n are M primary for n larger than 0. And the critical property is that II times ij is contained in I sub I plus j for all ij. This is the property which makes it possible to do something. Now, I will say that the filtration is Noetherian if and only if the graded ring I sub n is a finitely generated R algebra. Okay, so let's look at a few examples which are very naturally occurring ones. The first example is if I just take I to be a fixed M primary ideal. And I look at the filtration of powers. Okay, that's the classical example. Another example is if I take R to be a local domain and mu to be a valuation with value group Z, where I require that R to be contained in the valuation ring of mu. And if I take the maximal ideal, the valuation ring, intersect it with R, it's the maximal ideal of R, that the valuation dominates R. So there's the so-called valuation ideals, which I will write like this. I mu sub n is f and R such that mu of f is bigger than equal to n. And then I look at the filtration of these valuation ideals. Okay, so I'll look at a couple more examples. And the third example, which I guess there's an example 3. This is where you have R, an inclusion R to S, where of local rings, and you take I to be the filtration on R if you take powers of the maximal ideal of S and intersect it with R. Okay, and then we'll look at example 4, which is take R to be a local excellent domain. Okay, well, what does excellent mean? This is There are certain good properties which rings of finite type over a field, or integers, or completions of these rings, analytic local rings, all share, no matter how bad otherwise. And there's a list of theorems you see in your commutative algebra books about these things. And basically, an excellent rings are rings which satisfy all those properties. They're very technical conditions, but there's sort of one big theorem saying that all of the properties that you would think a reasonable ring would have, the excellent rings have. For instance, it's essentially the smallest category of rings where you can hope for resolution of singularities to be true. Okay, so let's look at even for this example, one could get by with a little less than this assumption, but it's a pretty big category, and then I don't need to be careful about adding extra assumptions and so on. So let's look at the case where I take the normalization of the blow-up of an M-primary ideal. Of the blow-up of an M-primary ideal. Now, this, using the excellent property, we know that this is this will actually be of finite type over R. And this is has exceptional divisors. With prime exceptional divisors, E sub 1 out to E sub R. And I have a valuation, nu sub EI. This is the valuation valuation ring OXEI, the local ring of that divisor. And the local rings of this type are called, the valuations of this type are called M valuations by Rees. I'll mention, well, I guess I don't need to write that. And these valuations are the Rees valuations of the ideal we just blew up. Now for A1 out to AR, positive or non-negative integers, and I can take a sum A1 E1 plus AR ER. This is an effective A divisor. So in other words, it may not be a Cartier divisor, may not locally be given by a single equation. Then I define IMD. This will be the sections minus M times A1 E1 minus M AR ER, and then I intersect with R. Okay, so if R is normal to begin with, you don't need to do this. And one can write it like this, as I of the valuation, the MA1 valuation ideal of nu E1, and you intersect it with this, and then you intersect with the the MAR valuation ideal of ER, nu of ER, and then of course the filtration, which I'll write like this, is IMD, and this is called a divisorial M filtration. Okay, and now if I go back and look at this, you can see, well, I didn't really need to bother with all of this geometry to define this, that I have right here at the top of the screen that I have these. And this, we could have just defined it like this right from the beginning. After all, these, I showed in example 2 how you define these valuation ideals. So I just take the intersection of it. But it will be useful for us to, in the proof, some of the proofs, to consider, make use of some information about the fact that it can be realized on a particular x. So, and in fact, there are infinitely many different x's. And even on the different x's, there's many choices of the ace of i's you can pick in here to get the same filtration. So what one says is that the pair of phi from x to spec r and express d is summation ai ei is called a representation of ID. Okay, so this will play a role more later on. But for now, let's consider which ones of these are Noetherian. Okay, so we know the first example, the one of the powers of ideals, this is always Noetherian, of course. It's, in fact, the algebra is generated in degree 1. But examples 2, 3, and 4 are often not Noetherian. Even in regular local rings, even in excellent local rings. Excellent regular local rings. Okay, so these are all examples which come up frequently in other things. So it's interesting to try to understand them and see if you can get any order out of them at all, or even going to the full generality of an abstract filtration. Okay, now let's go back to the classical case. This is the example 1, where I look at the filtration of powers of an ideal. And that one has been extensively studied, and there's some really beautiful results on this. So let's go back now to the case where we're still considering R is a local ring of dimension D. And I look at the case where I have a fixed M primary ideal. Now, we know that the length of R mod I to the M is a polynomial of degree D for M sufficiently long. This is the so-called Hilbert-Samuel polynomial. And we write this then where what's particularly important is the leading coefficient. And one writes it like this, with and then the first fact is that the multiplicity, as this is called, E of I, is always a positive integer. And this is the multiplicity of R with respect to I. Now, let's go back and look at this again in a way that that'll be more useful for our generalization of filtration. That for filtrations, such a formula does not hold. You do not get a polynomial. However, let's look at something that the fact that we can recover the multiplicity from this length in the following way, that we write the multiplicity of I of R with respect to I as the limit as M goes to infinity of the length of R mod I to the M, MD mod D factorial. And in fact, sometimes people define the multiplicity this way. And of course, the fact that this length function is a polynomial, that's why you know the limit exists. Okay, so first off, this is, I'll give a theorem about the existence of these limits and so multiplicities for filtrations. And this was something I proved a few years ago. Let's suppose that R is a local ring of dimension D. And let's take n of R hat to be the nil radical of R hat. Then the limit as m goes to infinity of the length of R mod I to the m times m to the d. This exists. Every m filtration I equals I sub m, if and only if the dimension of the nil radical of R hat is less than d. Okay, so this gives a necessary and sufficient condition for the existence of this limit on a particular ring for every m filtration. Now, one thing which I want to mention about this is you see this this condition about the dimension of the nil radical of R hat. Well, there are domains. For instance, Nagata gives an example of a actual domain R where its completion violates this condition, where the dimension of the nil radical of its completion is equal to the dimension of the ring. So the existence of limits can fail even on a domain. However, if you're on an excellent local ring, then the nil radical is actually just comes from the nil radical of R itself. So you don't have this terrible condition in excellent rings. But just let me say briefly about what this is, that because these are important cases. In particular, we see that limits always exist if R is analytically unramified. Which means that R hat is reduced. Or immediately one gets this from the theorem. Or R is excellent and just reduced. Okay, so say a little bit about the background of this, that the existence of a limit was proven in some cases by Ein, Lazarsfeld, Smith, and by Mustada. The existence of the limit is proven for local rings of closed points on varieties over an algebraically closed field by Lazarsfeld and Mustada using methods of algebraic geometry. All of the assumptions I just mentioned are used in their proof. They use the method of counting asymptotic vector space dimensions of graded families using Akunkov bodies developed by Akunkov, Kave, Khovansky, and Lazarsfeld-Mustada. We also use this wonderful method. The fact that the dimension of the nil radical of R is D implies there exists a filtration without a limit. This was observed by Dow and Smirnov. Okay, so let me give a simple example. Of something that very easily happens for filtrations. Remember, we had that nice condition that that multiplicities were always positive integers if you're looking at the filtration of powers of an ideal. But this fails completely for filtrations. So if I take just a power series ring and one variable over a field, and for a real number alpha, you take the roundup of alpha to be defined to be, well, just the roundup of alpha in R. So in other words, it's the smallest integer which is greater than or equal to alpha. So given a real positive real number lambda, let's let I sub n is the powers of x, which are the roundup of n times lambda. And I take I to be the filtration, I is equal to I sub n. And the multiplicity of I is the limit as n goes to infinity of the length of R mod I sub n over n, which is equal to lambda. So you see, you can, by this kind of trick, you can easily get any real number as a limit. In fact, I should have put down here something else. Yes, this is correct, actually. Okay, so I see that, okay, so in fact, in doing this example, I haven't told you what the multiplicity is. So let me correct that. That if I is a filtration, the multiplicity, you define E of I is equal to a limit as n goes to infinity of the length of R mod I sub n, n to the d divided by d factorial. This is a multiplicity of a filtration where when the limit exists. And we see, for instance, if we're on a analytically unramified local ring, that these limits will always exist. Okay, so this is the first part of it. Now, the next thing I want to talk about is mixed multiplicities. Okay, so I'll start out by reminding or informing you of a really wonderful theorem, which was by Bhattacharya, people and Rees, and also Rees and Teissier independently define these mixed multiplicities. So let's let I sub 1, I sub r be m primary ideals. Then for n1, nr natural numbers with n1 plus nr sufficiently large, if I take the length of R mod I1 N1 IR NR, this is always going to be a polynomial in N1 NR of total degree D. That's a theorem, of course. And you can, if we expand this thing, I'm going to distinguish the terms of degree D. And you call those coefficients the mixed multiplicities. So that's this homogeneous of polynomial of degree D, and then there's some lower order terms. And this part of, this is critical, write this back in. This part over here I'm going to give this a name. This is a homogeneous polynomial, which I'll, for the moment, I'll write like that. That's a homogeneous polynomial. Now these guys over here are called the mixed multiplicities of these ideals. And this notation, I think this notation originates with, well, certainly Rees and Teissier use this notation, and I think it originates with them. That there's actually a very nice book which explains a tremendous amount of the information in this subject about multiplicities and mixed multiplicities by Raina Swanson and Craig Unicke, where they give proofs of the construction of this. Okay, so the the critical point of this is that we reinterpreted multiplicity so that we could speak of multiplicities of filtrations. Well, we're going to do the same thing here. So what we observe is that this homogeneous polynomial is such that the limit as m goes to infinity of the length of r mod I sub 1 m and 1 I sub r m and r, and then I divide it by m to the d. Well, this is just going to be equal to this h of n1 out to nr. Okay, h is homogeneous of degree d, and everything else, the remaining terms have lower order degree. And this, in fact, now happens for all n1, n2, nr in the natural numbers, because this polynomial is true for all large enough n sub I. So if you multiply by a big enough m, it'll agree with the polynomial. Okay, so this formulation for this polynomial, this generalizes to filtrations. Even though the thing is not a polynomial, the lower order terms will be a complete mess. But this highest degree term giving this limit, this does exist. So this is a theorem from maybe a couple of years ago at this point. It's with Prangamas Sarkar and with Hema Srinivasan, where we did this when she was visiting us at University of Missouri, that this generalizes completely to filtrations. So let's suppose that R is a local ring of dimension D. Okay, well, we already know we can't get going, we can't even get started unless we have this nil radical condition. Okay, everything falls apart if we don't have that. But that's also a fairly mild condition. Okay, so now let's just take arbitrary filtrations, M filtrations. Okay, then we can look at the function Pn1 and R, and this is equal to the limit as m goes to infinity of the length of R I sub 1 m and 1 I sub r sub m and r divided by m to the d. And this is a homogeneous polynomial of degree d for n1 and r in the natural numbers. So for all natural numbers, you get a homogeneous polynomial. Okay, well, of course, at this point, going back, we and now we see we can define the mixed multiplicities of these filtrations, just mimicking what we did for the ordinary powers. So we write out this polynomial in such a way that it gives this. Okay, so we can write this as being, so this is how we define the multiplicities. We write this as equal to summation 1 over d1 factorial dr factorial times, maybe I should have started over here. d1 plus dr is equal to d1 1 over d1 factorial dr factorial times, this is how we define these mixed multiplicities. N1 dr nr dr, and this is how we define the mixed multiplicities of these filtrations. Okay, so in this formula, this enjoys these mixed multiplicities enjoy many of the classical properties that the mixed multiplicities for powers of ideals have, and in fact, in our paper, the paper with Sarkar and Srinivasan, we drive a number of these. And the one which is be useful for us later is the observation that the original multiplicity, in fact, this more or less comes from the definition, that this is just, or in fact, it does just follow from the definition, that this mixed multiplicity of ei to the d is the same thing as the ordinary multiplicity. In general, the philosophy is that properties which are involving, say, inequalities will always be true for arbitrary filtrations, but for equalities, it's much more subtle. And this is what I want to begin now talking about, the condition of equality. Okay, so let's look at, before we start this, there's sort of a subtle condition here which related to a theorem of Rees, which, and we'll maybe even go back to discussing this, this more at the end. But let's look at this situation, that if you want to compare multiplicities of ideals, somehow they're integral closures are important. So this is important here also, but it's a little more tricky. But let's start out looking at this. So if we look at a filtration, so then one can show that the integral closure of this ring in R of t is, well, I'll write it like this. I'll put an overline on it. That means the integral closure in R of t. This is, in fact, the summation of n bigger than or equal to 0, jn tn, where jn is a filtration consisting of all f and r, so that f to the r is in I n r for some r bigger than 0. This, I forgot to write that there, is in the integral closure of I n r for some r bigger than 0. So in the classical case, it's just, this is a well-known result. If I is M primary, then the integral closure of the powers of is just the algebra of integral closures. So it's a little different, but it's even for an arbitrary filtration, it's not a, you get a nice statement. Okay, so with this, I move on to, well, I'm going to give another, is this the time for this? Yes. I'm going to give another definition. So I'm going to say that an M primary and an M filtration I is equal to I sub n is said to be bounded if there exists a divisorial M filtration I of D such that R of I is equal to the Rees, the R is equal to R of ID, R of I integral closure. So I didn't define what this is. This is the direct sum n bigger than equal to 0 I sub n. And this is equal to the direct sum n bigger than or equal to 0 I dn. So the point is that this is always, for a divisorial filtration, this is always integrally closed in its in R of t. Okay, so this is a class of filtrations, which it includes the divisorial filtrations, and it also includes something else, which is that which is why we go to this, is that all filtrations of the form I sub n for a fixed ideal I are bounded. Okay, so what this does is the category of bounded filtrations includes the divisorial filtrations, and it also includes the filtrations from powers of ideals. Okay, so now we can go on to talk about this famous theorem of Rees. Let's suppose that I prime contained in I are M primary ideals, and R is formally equidimensional. Then the following are equivalent. Okay, well, the first condition is that the multiplicities are the same. And in fact, I'm going to state this the way, initially, the way Rees did, which is that the integral closures of them are the same. They both ideals have the same integral closure. Okay, well, we just looked at how complicated this condition, the correct generalization of this is we need to filtrations, we need to at least understand, it needs to capture this idea about these algebras being of the integral closures of their algebras being the same. So somehow we need to introduce another equivalent condition in order to generalize this. So if I take the integral closure of this algebra, this has to be the integral closure of this algebra, which as follows from what I wrote before, these 2 and 3 are equivalent. Okay, so another statement I might make here is that 3, well, maybe I should put both conditions here, is that 2 equivalent to 3 is always true. And the condition that, well, 3 implies 1 is true in arbitrary local rings. So you only need this formally equidimensional condition to ensure that if the multiplicities are same, then their integral closures of the ideals are the same. So we can already see that condition is a little more delicate. Now we have that this from the work we did with that I did with Sarkar and Srinivasan, that 2 implies 1 is true for arbitrary M filtrations. Okay, so if you've got the if the multiplicity, that if these algebras have the same integral closure, then the multiplicity is the same. So this is the direction, the 3 implies 1 direction, an analog of the 3 implies 1 direction. So, but we also show that 1 implies 2 is false for arbitrary filtrations. And a simple example of this is that if you take R to be a regular local ring, and I take I prime to be the n plus first powers of the maximal ideal, and that's contained in I, which is the nth powers of the maximal ideal, then one can easily compute that the multiplicities are the same, but they're not quite, the algebras are not quite the same. Okay, and this is a very interesting question about, well, what in the world, what is it? Can one actually give some sort of criterion for when these things are, what is an equivalent condition for the multiplicities? And in fact, there is one that I will give, but it's one where it doesn't seem to admit, and I would like to, it's a geometric condition, and it would be nice to understand what it means algebraically. Okay, so now now we come to this condition about these bounded filtrations, that it turns out that the Rees theorem is true for bounded filtrations. So let me state this, and this is from about a year ago. For this one, I think I can get by with a little less than this, but what I have right now is if R is an analytically irreducible or excellent local domain, and I1 and I2 are bounded M filtrations such that I1 is contained in I2. Okay, so this condition of, remember what bounded means. Bounded means that it's the integral closure of its algebra is the algebra of the divisorial filtration, and the algebras of the divisorial filtrations are always integrally closed. That one, that's and of course, remember, there's lots of bounded filtration. Then there are lots of bounded filtrations which are not Noetherian. So then the following are equivalent. The first statement is that the multiplicities are the same. And the second statement is that there is equality of integral closures of summation m bigger than equal to 0, I1 m t m bar, and this is equal to summation m bigger than equal to 0, I2 sub m t m bar in R of t. Okay, so this is exactly Rees's theorem after we reinterpret it to having this second condition as opposed to the third condition, which isn't valid for filtrations. Okay, so in fact, with our result with Brangama and Hema, that we showed that if there's a equality of integral closures, number 2, that implies 1. And we know that for arbitrary filtrations, 1 implies 2 is false, but for these bounded filtrations, these things are equivalent. Okay, so I will start to talk about Minkowski. Well, I think I'll be able to talk about Minkowski inequality. So that's also a really wonderful classical theorem. And they were proven by Teissier and Rees and Sharp. So the Minkowski inequalities for mixed multiplicities of M primary ideals in local rings were proven by Teissier and Rees and Sharp. Teissier had a number of conditions in it. I think the essential one was he was assuming the rings were Cohen-Macaulay. But these inequalities are also true for M filtrations, and we will see what they are. Also, I think Teissier I know he was very interested in the work of Minkowski, and he made an extensive study of them. And he was the one who realized that something like this could be true by looking at some, I guess, looking at the theorems of Minkowski within convex geometry. And he realized that such a theorem could be true in commutative algebra. Okay, so I'll just state this theorem. This is again from the paper with Brangama and Hema. And these are the Minkowski inequalities for filtrations. Let's suppose that R is a d-dimensional local ring with the dimension of the nil radical of R less than D. Now let's let I1 and I2 be M filtrations. Let's set, this is a classical notation for powers of ideals. It's the D minus I ith mixed multiplicity. Then the EI squared is lesser than equal to EI minus 1, EI plus 1, for 1 lesser than equal to I lesser than equal to D minus 1. So that's the essential inequality. Again, we need this nil radical condition for it to for us to even get started, to be confident that these limits always exist, or it's necessary for all those limits to exist. Okay, this is the essential one, and this implies a series of other inequalities, which I won't write down here, but including the most famous one, which is usually called the Minkowski inequality, which is this one, that E of I1, I2, 1 over D. Well, what is this? This is just a means of filtration I1, M, I2, M. This is lesser than equal to E of I1, 1 to the D, plus E of I2, 1 to the D. So this is the most famous one. You notice that this the so-called Minkowski inequality does not involve mixed multiplicities in its statement, although it can be, you can read off all three of these numbers from that polynomial, which gives the mixed multiplicities. So there was a proof of this for regular local rings over with algebraically closed residue fields by Mustada, not using these geometric methods, but in the generality here that we have, this is new in this theorem right here. Okay, so I guess we've actually reached a good stopping point. That what I will do next time is, we saw with this, there was the inequality. In fact, no, I wanted to say one more thing. So I think I will just finish with, did I say that? No, I said everything I wanted to, that these Minkowski inequalities, and these inequalities here are the classical ones for M primary ideals of Teissier and Rees and Sharp. However, the other direction fails. So maybe I should say that is, but no, I will say that next week. That next week, what I'm going to discuss is that when equality holds in this. And the first, so there's a nice characterization due to Teissier and Rees and Sharp and Dan Katz for when equality here holds here for M primary ideals. And that characterization does not work for arbitrary filtrations, but if you're within the category of bounded filtrations, the theorem characterizing when equality holds in Minkowski inequality generalizes exactly from the classical one for ideals. And that's what I will talk about. And I will also say a little bit about the, hopefully give an overview of some of the methods in the proof. Okay, so I will stop here then. And thank you for your attention.
Thank you, Dale. We are ready to take questions from audience.